Hello, engineers, and welcome to 2.1.2, which is Introduction to Structural Member Properties. We're going to be talking about beams today and how much they deflect. Believe it or not, when you load something, it could be concrete, it could be steel, it could be wood, whatever it is, there's always a certain amount of deflection. Like how much stretching is good and how much stretching, when does stretching become bad? Where things deform to the point where it's no longer safe. And, you just type in beam failure and you can find all sorts of videos. Like you can do analysis, you can look at how they break. But how do we as engineers guesstimate how much load a beam is going to have on it, and how is that safe, and how much will it bend when it does? So that's what we're going to talk about today is structural members. We're going to use that moment of inertia, and we're going to learn a couple of new things today. We're going to learn about what's called deflection, and we're going to learn about moment of inertia. So the centroids we talked about last time, how to find the center of mass of an object, and today we're going to learn about moment of inertia. So let's get going. Moment of inertia, it's a mathematical property that is related to the cross-section, and it's how stiff an object is. For instance, they have a diving board, which is pretty bouncy, right? Versus a diving block, which is not. When you jump off this, you want this to be rigid. When you jump off a diving board, you want that to be very flexible. How stiff an object is related to its shape. For instance, using a 2x6. This 2x6, 2 inches by 6 inches. That's how they call it. You always subtract a half. Don't ask me why. If you put it on its face and you stand on it, it's going to be really bouncy. But if you put it on its edge, it's not. A plank versus what we call a joist if you're into building construction. So why? How do we do that? What makes them different? It's totally related to the height. And to find the moment of inertia of an object, it's the base times the height to the third power. The height is 3 times as important than the base is when it comes to moment of inertia. So it's triple the important, not double, triple. Base times height to the third power divided by 12. So going back to that beam that we used on the edge as a joist, if you take its base times height to the third, and I think they use we use the letter I, XX, as the moment of inertia. Base times the height to the third power divided by 12. So the base, 1.5, the height, 5.5, and I'm getting these numbers from right here, divided by 12. 1.5 times 5.5 divided by 12 is 21. Now, this is inches. This is inches. Inches to the third power. So this is inches to the fourth. They are some really funky units for the moment of inertia. Inches to the fourth power. So this as a joist is 21. Let's calculate it for if it was on its side. We're going to do it the other way. Base times the height divided by 12. So again, the base this time is going to be 5.5. The height, 1.5. So 5.5 times 1.5 divided by 12 is 1.5 inches to the fourth power. So when you compare those two numbers, take a look at them. When they're right next to each other, 21 and 1.5, this is like a full 14 times bigger. So you're going to get a lot more stiffness, 14 times more stiffness out of that same object when you put it on its side like that. Why do we have shapes the way they do? Why do we have C channels, L brackets, I beams, solid beams? Because you literally have the exact same moment of inertia because it's the base times the height to the third power divided by 12. They have the same base. They have the same height, but they have less area and they have less weight. So you can get the same moment of inertia, but you can get it with less weight. There's a material property called the modulus of elasticity. We're going to learn more about that when we get into materials testing, but suffice to say, for right now, it's just how flexible an object is. There's a more, like, what's the word? Technical answer to that. You know, it's the slope of the stress versus strain curve, but I don't want to teach you what stress means. And I don't want to teach you what strain means right now in our journey. But just know that if you have a modulus of elasticity, they make a difference. So for instance, here's an example where you've got two beams. They're both the same size, but one is made out of Douglas fir, so a typical building material, and one is made out of ABS plastic. So you've got a plastic beam and you've got a wooden beam. And so what's really different, there's not much different about them as far as height, area, and moment of inertia, but what's different about them is that they have different what's called modulus of elasticities. How much they bend underneath load. And what we call how far they bend, delta max. Delta is a Greek letter. It means change. So delta means how far is that changing? When it is like deflecting and deforming, delta. What's the maximum max delta? How far it stretches. So we can actually calculate how far a beam is going to deflect through this equation right here. So how far a beam deflects, it depends on the force. If you put 100 pounds on it or if you put 1,000 pounds on it, 1,000 pounds is definitely going to stretch it more. L represents the length. So the longer a beam is really important. It's 3 times as important. E represents the modulus of elasticity. And so you can see ABS plastic has got like 1/4 of the modulus elasticity of the Douglas fir. And then I represents the moment of inertia. So that's related to the shape. So it depends on the shape, depends on the length, depends what it's made out of, and it depends on how much you're pushing on it. That's what each of these letters are kind of saying. So we're going to actually calculate how far a beam deflects. And this is an activity we're going to do in class. Is I'm going to give you all 2x4s, and you're going to calculate how much it deflects, and then you're going to see if it deflects that much. And we can tell each other's weight by how much the thing deflects. Or we can calculate the modulus of elasticity for our different pieces of wood. So here's the question. Calculate the beam deflection for beam A. So what you're going to do, you're going to take the force. We are putting 250 pounds on it. So that's F. 250 pounds. And then the length. The length of this thing is 8 feet. So I want to make sure, take a look, gang. This is in inches. This is pounds per square inch. We need to make 8 feet. We have to put that in inches. So we're going to take 8 times 12, which is 96. Got to watch out for your units. There's a lot going on here. Just don't blindly put in your numbers. Take care to look at your units. 48 times E, and E is the modulus of elasticity. So it's 1,800,000 pounds per square inch. And then multiply by my shape. That's 20.8 inches to the 4th power. Now, this gets crazy with units. So 4 of these cancel 2 of those. And then also, I have 2 left over, so I have 1 left inches at the top. This pounds cancels off this pound. So when you do all this stuff, it ends up in inches. Just trust me if you don't follow what I did there. But that's how far this thing is going to deflect is measured in inches. So when I multiply 250 times 96 to the 3rd power, divide by 48, divide by 1.8 million, divide by 20.8, you end up with 0.12 inches. This beam is going to deflect about 1/8 of an inch, because 1/8 of an inch is 0.125. So this thing's going to flex 1/8 of an inch. We're using a 2x6, putting a pretty substantial load on it. It deflects 1/8 of an inch. Not bad. Now let's do the exact same thing for that ABS beam that we had talked about. Same force, 250. I'm going to skip the units now. The length, same length, 8 times 12, 96. 48. Modulus of elasticity, 419,000. Now see, we're not dividing by a big enough number, so we're going to get a larger number in the end. Just my math brain thinking ahead here. And then the modulus of elasticity is 20.8. So multiply all those, you get 0.53. So this is about 1/2 of an inch. So our other beam deflected 1/8. This deflects 1/2. You know, that's like 4 times the deflection in these two beams, just because of the material that it's made out of. So, beam deflection, it depends on 4 things. It depends on the force. How much force are you putting on it? The more force, the more it deflects. Depends on the length. Really depends on the length. That's the most thing that it depends on. It depends on the shape. That's what the letter I represents, the moment of inertia. If you remember, it was base times the height to the 3rd power divided by 12. And then the modulus of elasticity, what it's made out of. The shape, what it's made out of, the length of it, and how much force you're putting on it. Thanks, guys and gals. Have a nice day.